And guys, so today we want to discuss what we call quantum numbers. So if we think back to Bohr's model, we remember that an orbital is the three-dimensional region within an energy level or surrounding an atom where there is the probability of finding an electron. Okay, so we draw these simplified Bohr models with rings. We know that atoms aren't flat and two-dimensional, they're three-dimensional. So quantum numbers really specify the properties, okay, of an atomic orbital and the electrons within them. So think about this as not really a zip code for an atom, but something similar, something like an address. Okay, it tells not only where it's likely to be, but based on where it is, we can learn some properties about that. Okay, so in this video, we're just going to discuss the 4 quantum numbers. I talk about their names, their symbols, and what we really learned from them. Then in another video, we'll talk about how we determine the quantum numbers and what an electron's specific set of quantum numbers really can tell us. Okay, so our first quantum number we call the principal quantum number. So what this quantum number does is it defines the electron's probable distance from the nucleus. Okay, so it also describes the size of an orbital. So if you think about an atom in the simple terms of the Bohr model, the further away from the nucleus you are, the larger the orbital was, the larger the ring was. Okay, so we can use both definitions there. Primarily we use this to describe the size of an orbital. We think about that in terms of distance from the nucleus as well. So the symbol for the principal quantum number is n. Okay, so n has to be an integer, so it can be 1, 2, 3. We typically think of it stopping at 7. I can actually go further, we'll discuss in the next video, but for now let's just say 1 through 7. Okay, and really when we think about the principal quantum number, we think about which of those energy levels. Okay, so which of those rings from the Bohr model is the electron located on. Does it have a principal quantum number of 1, so it's on the lowest energy level, a principal quantum number of 3, meaning it's on the third energy level, or so on all the way up to 7 or higher. So next we have the angular momentum quantum number. So within each of the principal energy levels described by the first quantum number, we have what we call sublevels. So smaller levels within that main level, the 1, 2, 3, 4, 5, 6, 7 levels. Each of those have smaller sublevels. So the 4 types of sublevels that we have are called S, P, D, and F. So the difference in S, P, D, and F are their shapes. Okay? So the angular momentum quantum number, its name isn't really very descriptive here, but it describes the shapes of the S, P, D, and F sublevels. Okay? So if you think about the S sublevel, its shape is spherical. So a nice little ball surrounding the nucleus. So the P sublevel is dumbbell shaped. That's how you spell dumbbell. You can correct me if I'm wrong. D we refer to as double dumbbells. And F is overlapping dumbbells. Okay, so I'm not even going to attempt to draw these. You can look at the attached graphic to get a better idea of computer generated what these shapes look like. So these shapes are defined as the area that has a 90% chance of containing the electron. So we know that electrons move around quite a bit, and with modern chemistry we look primarily at predicting the area where they might be. Okay, so we can't guarantee that they're in this area, but based on these shapes we know that there is a 90% chance of having that specific electron within that area. Okay, so at this point we want to go ahead and more specifically define the term orbital. Okay, so an orbital is an area that holds 2 electrons. Okay, so an orbital is a very specific area that can hold 2 electrons. So if we think about these sublevels and how many orbitals they have, the S sublevel has 1 orbital. The P sublevel has 3 orbitals. The d sublevel has 5 orbitals. And the F sublevel has 7 orbitals. Okay, so if each if each orbital holds 2 electrons, that means the S sublevel can hold 2 electrons. P can hold 6 electrons. D can hold 10 electrons. And F can hold 14 electrons. So we'll come back to that idea and discuss it in more depth in a moment, okay? But for now, be aware that the angular momentum quantum number describes the shape of these sublevels that exist within the principal energy levels. And the symbol for the second quantum number, the angular momentum quantum number, is a cursive L. Okay, so the third quantum number is the magnetic quantum number. It's a little bit easier to think about. The magnetic quantum number describes the axis of orientation for each sublevel. So if you think about the P sublevel, and it is dumbbell shaped, so I'm going to attempt to draw it like that. It could be oriented along the y-axis vertically, along the x-axis horizontally, or along the z-axis coming in and out of the page. Okay, so this number simply tells us how is the sublevel oriented in relation to the nucleus. So the abbreviation we'll use here is M subscript L, so M sub L. So the last quantum number that we'll have is the spin quantum number. Okay, so all electrons have a spin value. Okay, so electrons always pair with an electron that has an opposite spin. So we assign this spin value as -1/2 or +1/2. So you think about this as up or down. You'll typically see the +1/2, okay, notated with a up arrow, and the -1/2 notated with a down arrow. Okay, so the 1/2 is just kind of an arbitrary number to show us if an electron spins up or spins down there. The symbol we use here is M sub S. Okay? So those are the 4 quantum numbers that we use to describe the location and some of the details of an orbital and the electron within it. So let's go back now. I know that was a lot and you might be kind of confused. Let's just kind of summarize what's going on with these electrons right now and think about what's going on within these atoms. So let's look back at the basic Bohr model. And we have these rings. Okay, so these rings we refer to as energy levels. Okay, so what I'm doing right now is I'm just going to tell you how we organize electrons, the terms we use to describe it, kind of summarizing the quantum numbers. And I'm going to go from the most generic area at the top to the most specific area at the bottom. Okay, so the energy levels are just the rings, okay? So we can have the first energy level, we can have the second energy level, we can have the third energy level, and so on and so forth, okay? Then within each energy level, so let's just pick, whatever energy level it might be, we have sublevels. Okay, and those sublevels are S, P, D, and F. So the energy level, or the principal energy level, told us how far away the electron was from the nucleus. Okay, the sublevel tells me what kind of shape the orbit, what kind of shape the path the electron takes around the nucleus is. Is it spherical? Is it dumbbell shaped? Is it double dumbbell shaped? And so on and so forth. And then we know within sublevels we have a more specific unit of organization. We have orbitals. Okay, so orbitals only hold 2 electrons. They can have 1 electron or they can have 0 electrons, but they can't have more than 2 electrons. And when they have 2, they have one that spins up and one that spins down. They have opposite spins. Okay, so for every single electron, it is in an orbital. The orbital is within a sublevel, and the sublevel is within an energy level. Okay, so you can think about this as kind of more of an address for an electron. An orbital might be the house number. A sublevel might be the street name. And an energy level could be the city or the state. So you think about more specific descriptors on the exact area of an electron. Okay, So there are some specific rules about what sublevels go in what energy levels, and how many orbitals go in sublevels and energy levels. So we'll discuss that in the next video, but for now I just want you to have a basic understanding of what energy levels are, what sublevels are, what orbitals are, and what each of those three tell us about the location of an electron.